With applications to two problems. The one will be forecasting of electricity consumption, and the other one will be the forecasting of exchange rates. Okay, so first slide gives you all the keywords. So the framework of this talk is, and list of keywords is there, sequential and worst-case deterministic prediction of time series based on ensemble forecast. So many keywords, and we'll go over each of these keywords individually. So your mission as a statistician or machine learner is to predict a time series, y sub 1, y sub 2, and we'll do that in a sequential fashion. So ensemble forecasts are available, and so these are base prediction, and they can be given by stochastic models, some machine learning methods, etc. But for us, these will be black boxes. So we have a bunch of predictors, and we don't try to understand where they come from. And they can come from very different backgrounds. And actually, the more different, the better. So at each instance, each of these forecasting black boxes processes past observation and gives you a prediction. And we're playing in a sequential fashion. So more precisely, the setting is as follows. The prediction y sub hat of the next outcome at y sub t is determined based on the past observation. So you can have a look at the past observation. And based on the current and past ensemble forecast. So why the current forecast? It's because you believe in your forecasting black boxes. Sometimes they are called experts. So you believe that they are good. So you rely on the current forecast. And why do you also rely on the past forecast, S less than t minus 1? It's because we all have a tendency to compare the past forecast made to the past observation, and will believe more the expert that performed better in the past. Okay, the rest of the talk will simply quantify this intuition. So a typical solution, an easy solution, is to form convex or linear combination of the ensemble forecast with weights that will vary over time depending on the performance. So I denote by y sub hat the convex or linear aggregation of the expert forecasts. So the distinguishing feature of this sub-theory of machine learning is that the observations, y sub t, will not be considered the realization of some stochastic process. So the game will not be to estimate the parameters of the stochastic process to form good predictions. We will simply not model the y sub t. Hence, there will be no ground truth, and hence there cannot be any absolute criterion of performance. So our criterion for performance will be a relative one. And the relative criterion will be given by the performance of the best forecasting black box, of the best constant convex combination of the forecasting black box. Okay, but before I describe that, I need a loss function which I assume to be convex in the first variable, so for instance the square loss, but we'll see others. And based on this, I will be able to define cumulative losses. So the cumulative loss of the statistician, that's us, is a sum of instantaneous losses. And the instantaneous loss at round t is the divergence as measured by L between our aggregation and the true observation. So that's our cumulative loss. And for each of, say, the constant convex combination Q, I can also define a cumulative loss where the aggregation is performed at each step according to the same convex combination. So there's no dependency in T here. Okay, my aim is that my cumulative loss be as close as possible to the best of these guys. And actually, the key quantity is the difference between these two quantities here, and it's called the regret. And it measures how much you regret not having aggregated addition according to the best Q. And as promised, there's no stochastic modeling assumption. So the regret, I will control it in a very robust way by putting a soup here over all possible sequences of observation y sub t and all possible sequences of ensemble forecast f sub jt. So it's not just over most of these sequences or the typical ones, it's over all possible sequences. And take an average, and I want that this slim soup be negative in the limit. We'll see that typically the regret will be something like root t. Okay, hence the name of that subfield, prediction of individual sequences or robust aggregation of ensemble forecasts. And the difficulty, just to point it out again, is that the best convex combination Q here is known only in hindsight, and it can even, and of course it changes over time, while we have to predict in a sequential fashion. Okay, so it's a sequential fashion that is a difficulty. To sum up, let me give you a reinterpretation of all these terms in more classical, in a more classical statistic way. So we're actually doing metastatistics. So that way, the code, the color code for metastatistics on this slide will be pink. The ensemble forecast, color code blue, they are given by statistical forecasting methods or machine learning methods, each possibly tuned with a different set of parameters. You know that in practice, tuning a statistical method is usually a nightmare. So instead of trying to find a good set of parameters, you can construct several clones of your method, each of different parameters, and then aggregate the forecast. I mean, that can be a way out of the difficulty of tuning the parameters. And then you combine this ensemble forecast, which rely on possibly on some stochastic model, but you combine them in a robust and deterministic manner. So at the aggregation stage, you forget any possible stochasticity of the data. You don't use stochasticity twice. Okay, what I said in words appears also in this formula. So the cumulative loss of the statistician equals, by definition of the regret, the performance of the best constant convex combination Q plus the regret. And then you can see that the cumulative loss can be decomposed as an approximation error, how good your ensemble forecasts are, plus a sequential estimation error, which is exactly the regret. So that should be reminiscent of the bias variance decomposition in classical statistics. Okay, disclaimer for the rest of the talk. Of course, when you aggregate in practice, you usually don't aggregate with the method I'll present. Usually you use BMA, count, random forest, etc., which even if the data is sequential, you use in a sequential way, while they were only designed for the batch case. Okay, so people rerun the whole procedure from scratch and to get the next prediction. So you actually don't get real online guarantees. So as a comparison, I will present algorithm with real online guarantees. And we'll see that when it comes to calibrating the parameters of the method, we won't use methods like cross-validation, which you typically use for all those fake online methods, but we'll have proper online tuning methods. Okay, first study, forecasting of electricity load. So I'll actually be presenting the work of Pierre Gaillard, a PhD student of mine that defended in July 2015. So he did many things, but I'll take the simplest case, the simplest study when he only considered an ensemble forecast with 3 methods. And then he tried to improve by bagging and boosting to produce a bigger set of ensemble forecasts based on these 3 base methods, etc. So he worked on the approximation error, but I won't be presenting that. I will only present the results that we get based on the 3 ensemble forecasts. So he did much more, but I just want to illustrate theory in a simple way. So data set, we have 3 years of training data, and then 1 year of testing set. So 3 years, during the 3 years, you train your method and tune the parameters, and then you use them in an operational way the year after. So every day they do prediction, but you can't touch the methods anymore. we have to predict the electricity demand for EDF clients at a half-hour step. And typical values that you should keep in mind is that the electricity consumption is of the order of the typical order of 50,000. And you see that the root mean square errors of our method will rather be around 1,000. So the methods are really, the base forecasts are really excellent. The difficulty here was to be more excellent than what was already excellent. And the three forecasters, I'll present them in slightly more details in 2 slides, are a general additive model, a curved linear regression model, and a kernel wave function model. So, and again, instead of trusting only one model or base forecaster, instead of picking the method of one of your colleagues and having the 2 other colleagues being disappointed, you take the prediction of all your colleagues, welcome, 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 and you aggregate them. And we'll see that actually considering the 3 forecaster is more efficient than just considering 1 or only 2. But it's a very ecumenic method. Okay, so data looks like electricity consumption. So more electricity is consumed during the winter because you have to heat, and during a typical week, more electricity during the week because industries work. And the convex losses that we'll pick are the square loss, and this will lead to the root mean square error, and the absolute percentage of error, x minus y divided by y. So that will be the mean a posteriori error. And the operational constraint is that we have to do 1 day ahead prediction, so predict the 48 next time instances. But I won't bug you with this operational constraint. So as promised, the forecaster, so one is, so the general additive model has been constructed by Wood and then imported at EDF by Yannick Good. So curved linear regression was built by this set of people, so Yannick Good and Xavier Brossard work at EDF. And then functional wavelet kernel approach was constructed by Anestis and Antoniadis and Jean-Michel Poggi and Rairo Cugliari doing his PhD thesis in collaboration with Xavier Brossard. Okay, so these will be, so these 3 forecasters were built by people of the R&D team of EDF in the previous year, and we try to see whether we can improve on them. Okay, so this slide will show you that there's hope for improvement, and then we'll see whether we can achieve this improvement. So so there's a slight typo here. It should be divided by y sub t. So I'm considering root mean square error and mean a posteriori error, so divided by y sub t here. And the first thing I do when a partner asks me to work on a new data set is that I want to check for potential. So it trains the experts of course, we do that on retrospective data because we don't have time to wait for the next 2 years. So it brings the historical data, we take a training set and we construct the ensemble forecast, and then we test it on the data, on the last quarter of the data. So we compute the performance of each forecaster and see which performance the best forecaster achieves. Then we also compute the performance of some naive methods like the uniform average of the forecaster. And then, so just to get a first idea of how good the experts are. And then our real targets would be getting close to the performance of the best constant convex combination or best constant linear prediction. So in these 2 cases, these aggregations are better than the naive method or the best forecaster. Note that you don't know in advance which is the best forecaster. So even achieving the performance of best forecaster is sometimes a challenge. But still, I mean, then I asked the partner, would you be satisfied with getting close to this performance? And if she or he says no, then we stop. I mean, I don't work on the data set. Otherwise, if she or he would be satisfied with this performance, then I usually know that we can get close to it and that things will be well. Okay, but we first do this sanity check just for everybody not to lose time. So actually, in the article I mentioned of Pierre, the focus is to create more forecasting methods by bagging, boosting, etc., to reduce these approximation errors. So it really works on lowering these numbers. So I won't be presenting that. I will just show you how to get close to this performance. Okay, strategy. So I promised strategies. I'll show you two. One that does convex weights, and another one that you all know, ridge regression, that does linear weights. So the novelty for you will be that ridge regression, designed in the 70s for a stochastic world, also works in this individual sequence world. Fantastic, right? So let's do some math with the first strategy. Short recap of the notation. We have a loss function. We need to sequentially choose a convex weight. And the aim is to bound in a very uniform way the regret, which is defined as the difference between our cumulative loss, the sum of instantaneous losses between our aggregated forecast and the true observation, compared to the performance of the best constant convex Q when you aggregate addition according to the same Q. There are different ways of bounding that. Actually, if the loss function is strongly convex in Francis' sense, you can get log t upper bounds over that, but I only deal, for simplicity, with the case of convex functions. So for convex functions, we'll do a reduction to the linear case through a convexity inequality. What in French we call the slope inequality. I don't think that in English there's a name for that. Okay, by putting the gradient into the picture. Okay, and that assumption is okay for all the losses that I described. So that will be our technical argument. So let's use this technical argument, and we'll read each of the lines slowly. So we start with the definition of the regret, except that the mean that was here, I put in front, becomes a max. So here, minus L is concave, so you have the max of a concave function. The max is achieved in the interior of the simplex. So this problem really has the difficulty of a continuum, because you need to consider the whole simplex. Look at the last line. We will go to a finite problem with only finitely many elements to consider. Okay, so there will be some simplification at some point. So simplification actually arises here when you apply the convexity inequality. So I have the gradient inner product with this difference. And the blue quantity here, I denote, I use a shorthand notation, L tilde, J sub t, it's like a pseudo-loss. So it's a mere, from here to here now, it's a mere rewriting, just using my notation for the pseudo-loss, and that problem now is linear in Q. So the maximum is achieved in a corner of the simplex, so it's a max of finitely many elements, which I put inside, it becomes a mean, and I reduced the first problem to a linear problem. And now I'm in a very abstract setting, and things can be done. So that's a summary of the previous slide. So modulo the pseudo losses, I need to control that linear regret. Okay, everything is linear it's linear in your prediction. Okay, to do that, the algorithm is called exponentially weighted average forecaster. So I should point out that one thing that doesn't work would be putting all your probability mass on the best performing expert so far. So that typically has a linear regret, so you have to smooth out the strategy. So you're putting, of course, much more weight on the best performing experts and the best performing experts, actually, but not all the weight. So we do that through some exponential rewriting. So the probability mass or the weight mass associated with J is e to the minus and then cumulative loss of pseudo-loss. Okay, so because it's e minus eta, most of the weight goes on the best performing expert. And then modulo this exponential weight, the regret is bounded like that. In a minute, we'll optimize the bound because everybody is already optimizing the bound. We'll get a root t. But let me just show you the proof. And I won't go into the details, just to show you that it fits on one slide. Okay, and the key element is this inequality. It's actually called a Hövding's lemma. And the rest are just simple manipulation, telescoping sum, blah, blah, blah. Very easy, but we won't describe it. The slides are on my webpage. You can read them tonight if you wish. But tonight it's a bouillabaisse. I'm sure you have better things to do. But let's try to optimize the bound. So we still have some hyperparameter ether. I know, it's disappointing because I promised that you could aggregate statistical methods that you had difficulties to tune, and still there's a parameter to be tuned. I know. But let's see in theory which ether we would pick. So if you optimize this, the optimal choice is here, you would obtain this bound. So that's the range of the total losses, that's the number of rounds, and that's the number of members in the ensemble forecast. So there are two good news. First good news is that you get a little O of t as expected. Second good news is when it comes to the dependency of the number of experts in the set. It's only root of log n, which is a constant, as everybody knows. So where's the catch? So in principle, you would have an incentive to put more and more and more members in the set of forecasts. But the catch is that they need to be different, otherwise there's no point in aggregating an army of clones. And that's difficult. I mean, it's difficult to build many experts that are very different, the ones from the others. Okay, but in theory, everything goes well. But there's a bad news. The bad news is in the ether that is optimal for theory. It depends on the number of rounds, and sometimes that you don't know it in advance. It depends on the range of the losses. Sometimes you don't know it in advance. Plus, and that's the worst part, it doesn't work in practice. Okay, there's some gap. In practice, you usually want ether to be slightly larger, like 1 or 2 orders of magnitude larger. It's always, the usual rule of thumb is take the optimal parameter and multiply it by 100 or 1,000, and then in practice it works. Okay, so there are theoretical solutions. People have been writing lots of articles about it, so the doubling trick, adaptive learning rates, ether30 that depend on the path picked according to some complicated theoretical formulas, etc., etc. Of course, none of that works in practice. So, how do we do in practice? So I'll show you how we do in practice, and for a long time I had the hope that we could prove a theoretical bound for it, and Pierre Gaillard showed to me that actually we can prove that it sometimes has a linear regret. So it's still an open problem for us to find the bridge between theory and practice, find a natural way of calibrating this parameter that works in practice. Okay, so it's still our main open problem. But in practice, how we do is the following, and note how different this is from cross-validation. But we'll be exploiting the sequential fashion. Suppose you have an infinite computer power, and you can run all the exponential weighted strategies for all possible values of eta in parallel. Okay, of course you can't. Usually you take a grid, but suppose you can do. You denote the cumulative loss of one strategy calibrated with eta by L hat sub t of eta. And then, for the next stage, you predict as a strategy associated with parameter eta sub t. So you still do some exponentially weighted average prediction. So you're still smoothing out the things. You're not putting all your weight on the best performing experts. But the parameter you pick as the parameter that performed the best on the past. So in some sense, you train the parameter on past data. So you resort to the strategy that performed best in the past and predict according to it. Okay, that works well in practice. And sometimes on well-behaved data sets, the eta sub t converge. So during the first quarter of a third of the data set, it varies, and then always the same value. but we don't know why. Don't ask me why, I don't know. Okay, other natural variants that people, statistician audiences sometimes objected to the method, because what they disliked is that you use all data from the origin of time till yesterday. So usually statisticians dislike that. Why don't you use moving sums? You only consider at most the age-past data. So a student, an MSc student of mine could prove that the regret is linear in the worst case. Okay, that was expected, but I never had the courage to prove it. So not a surprise. But still, there was an interesting idea, which is that you should trust more the most recent losses. I mean, what happened in the ancient Rome shouldn't matter that much. So what you can do, you can discount the losses. You put more weight on more recent losses. So this is a decreasing function. So when t minus s is small, that is when s is close to t, this is larger. Okay, for this discounted version, we can prove regret bounds under some assumption on the discount and on learning rates and blah, blah, blah. So we usually take 1 over t minus s squared in the experimental studies. And actually, this bridges between moving sums and the original version. And it actually performs better than the two others. Okay, now a strategy we're done with convex weight, we're turning to linear weights. So you all know the ridge regression. And actually, the same strategy exhibits a sublinear regret for individual sequences. So a regret less than this quantity, which depends on the regularization factor. But if you take lambda of the order of 1 over root t, this becomes a root t. I mean, the bounds that were proven here, and then in the book by Nicolo Cesamianchi and Gabor Lugosi, they were actually slightly data dependent, but in a subtle way. So everybody believed that the regret was logarithmic, and Sebastian Gershinovic, a former PhD student of mine, he objected. He said, no, there's something strange going on, and he found the root t upper bound. So, same comment as before. When you have to tune lambda, you can use the same procedure, and this is also a good strategy. So another upper problem for those interested is that, of course, nobody nowadays resolves to ridge. Everybody does lasso, right? So question is, can you get such an individual sequence bound when you replace this Euclidean regularization by an L1 regularization? Okay, so for the time being, we tried a bit. We never tried for a long time, but I mean that's a clear idea for an article. But I don't know how difficult this is. Okay, let me skip these comments because we are running out of time. So back to prediction of electricity load. So just recalling in that table the hopes and how good the experts are. So this is performance of the best expert. This is performance of the uniform aggregation. You want to outperform that, because otherwise, if your method is only, say, 1% better than the naive method, there's no point, right? And the hope is that the best constant convex combination, the best linear aggregation, improve performance by, say, 10 or 15%. Okay, so what do we get? So without discount for simplicity, the exponential weights with the best, okay, it doesn't work anymore. So with the best parameter in theory gives you 644. And then when you pick the best eta on data, but that's cheating. I mean, you run, but that you can do because it's retrospective. So you run all exponentially weighted strategy with different etas, and you pick the best eta on the data. Okay, but still, you want to know how good this strategy is just for the sake of knowledge. So 619, and actually with our strategy that picks eta sub t depending on past performance, you get close to this strategy that cheats. Okay, and in any case, we get slightly better than what theory says. Theory says that you should get close to the best constant convex combination, and we slightly outperform it. So we were happy with that. And then later on in his PhD, Pierre introduced a forecaster called ML Poly that, for the first time, has good practical performance with a theoretical tuning. Okay, that's one of the main achievements of the PhD. I mean, something that works in theory and in practice. Okay, let's look at the weights. So these are the weights for three strategies. So exponential weight as tuned by theory, exponential weight as tuned with the best eta on data, and ML Poly as tuned in theory because it works in practice. So I'm not giving you the color code because we did that once, and when people are people then tend to think that the method, for instance, the blue method, the one that whose weights converge to 0, is a dumb method, and people might be offended. So I'm not revealing you who is who, and I'll show you on the next slide that everybody is useful. But still, let's look at how the weights evolve. You see on the first graph, they evolve very slowly, very slowly. And then they are more active on the second one. And the third one is interesting because you see that some experts sometimes can die, and then they come back to life when needed. Okay, so our methods are reactive to changes. That's the idea that I want to sell you. And it's important to have many different experts because sometimes they're miserable, they fail, they disappear, but they can come back if needed. Okay, and the weights do not converge. We often get questions by economists that whether the weights converge to the ground truth or etc. No, there's no reason for that, and it doesn't happen. It just doesn't happen. Okay, are all three forecasters useful? Yes. If you only take the best two forecasters and do the same aggregation, you lose each time a bit, right? So that's in line with what all I told you so far. And now we can take a look to what Ridge does. So Ridge does something of the order of 635 here. Forget about these lines because I need time to tell you about this. And the weights picked by Ridge are smoother, actually. Right? They tend to converge, and that's sometimes something that we observe with Ridge. Sometimes they converge. Okay, but that was only a small glimpse into the work performed by Pierre Gaillard in his PhD thesis. The thing is that he tried many other data sets, like a Slovakian demand for clients of an EDF sub-branch, to competition about predicting electricity price or electricity load, the heat load of a Ukrainian cogeneration plant, electricity demand for subgroups of EDF clients, always with these methods, and it always worked very, very well. I just want to point out the universality of the aggregation methods. So all these are electricity-related data sets, but it also worked well with the forecasting of air quality, the forecasting of production of oil reservoirs, the production of exchange rates. So it's a very generic method. Actually, I'm not sure I've already seen it fail. So methodological summary. So I'll explain to you how I proceed when industrial partner comes with a data set and a field for application. So usually it comes with n-based forecaster and n-based forecasters that he trained on the data set, and I asked him to pick another data set for the evaluation. Then we compute some benchmark, like the performance of the best expert, the performance of the uniform mean of the experts, and then oracles, like the performance of the best constant convex combination, etc. And I ask him, would you be satisfied with this performance? If he or she says no, then we stop. Otherwise, we go to point 3. Point 3 is that we hire a student, and she or he evaluates the strategies when run with fixed parameters, because that's easy to do in the first time. So if we're happy with the performance of the best parameter in hindsight, we go to step 4. Step 4, we do that data-driven meta strategy that picks a parameter according to past data, and that's the result of that we would have obtained if we had proceeded in an operational fashion, if we really had to deal with the data day after day. Okay, so, and if step 4 is okay, then we go to step 5, which is writing a paper. So typically, we expect the number of instances of the training set to be larger than 5 times the number of experts or 10 times the number of experts. That is, unless we have one day a lasso type methods. In that case, maybe T can be of the order of n or 2n or something like that. But for the time being, we can't select a subsample of the experts. And hope usually, I mean, people are usually happy when the oracles or the final results are 10 or 20% better than the methods used so far. Okay, probably not the time to discuss exchange rates. Do I? That's all? It's probably over, right? I should conclude, no?
10 minutes.
What?
Yeah. 5 or 10.
No, you sure? Well, let's do it in 3 minutes then. So based on some macroeconomic indicator for each pair of country, we try to predict the exchange rates. And usually it's difficult to, so we do monthly average prediction rate, and usually the benchmark in that literature was the average of the previous month, because exchange rates are modeled by Brownian motions. Okay, then economists did complicated formulas, and they added more indicators, but always aggregating them with ordinary least square regression. I know that for all of you, it's a scandal that they still do regular or non-regularized OLS. They should at least regularize them because they overfit otherwise. But to them, it was, I mean, to them, they don't revisit the aggregation layer. They only work in putting more macroeconomic information as input variables, but they don't work on the aggregation layer. And we try to work on that aggregation layer, and by using the most fundamental macroeconomic variables that were already considered at the beginning of the 80s. Okay, so there the literature only worked on the approximation error, totally discarding the sequential estimation error, and we just say, hey, people, stop working on that approximation error. Well, it's useful, but stop devoting all the energy to that, and spend also a tiny fraction of your time on the aggregation error. Okay, so still root mean square error, and we predict the exchange rate as, the log actually of the exchange rate as minus the value of the previous month as a linear combination of those macroeconomic variables, and we consider regression and exponential weights. So you have some orders of magnitude for the data. So data was for the last 40 years. And what you should take a look at is this slide. So these are the performance of the economic indicator. These are the oracles. And this is what economists were typically doing. So ordinary least square error over the past 10 years and with in a rolling scheme, so with a moving window. So that gives you a performance that is worse than the random walk benchmark, than predicting the next month with the value of the current month. And if you visit the aggregation layer as we did, then you get 2% or 3% improvements. And these improvements are statistically significant. And same for, so that was for USD and GBP, same for the yen and USD. Okay, and actually we did that for 12 currencies and other sets. I mean, it's very, very robust. Okay, quantile prediction I'm skipping. And conclusion, you can do other data sets. If you have a good data set, I'm always willing to listen to you and to work with you. And time is over, so I'm give you the references, the Red Bible, the book by Nicolo Cesamianchi and Gabor Lugosi. Thank you.
Okay, so questions?
You consider as a main model of your data is a stochastic time series, in fact. It is well known that the predictability is dependent on the property of this time series. For example, for white noise, it's impossible to do any forecast. And as a measure, we may use of the predictability, for example, empirical entropy. The less entropy, the better forecast. Your estimation of accuracy, it's possible to connect in some way with entropy, or you don't consider this?
I'm thinking of the upper bound and lower bounds, how we prove them. There are entropy terms, but like the log n, the entropy is because we with the entropy of the starting weights. So I guess if you have information on the starting weights, don't start uniform, then you get some entropy term. But I'm not sure I can connect it to the entropy of the whole process. But it's a good question now. Think about it.
Gilles?
Just wanted to ask a curiosity question. So, on the financial data, you improve prediction.
Economic data, because it's monthly averaged.
Sorry, economic data. It was then better than the prediction, constant prediction from last month. I mean, what you obtained. It was, I guess, the improvement was kind of modest, but then it was enough to be better than.
NC is no change. It's a left top. NC.
Yes, okay. Sorry,
That's no change. No, but I went very fast. But the improvements are with respect to that benchmark, which was deemed impossible to beat or difficult to beat.
Other questions? Okay, you know I'm not a specialist about this topic, but we may have the impression that it may be very expensive from a computational point of view to take all the data to do the forecast. And you mentioned in your talk a method based on the sliding window, capital H. Are there some automatic procedures to choose this sliding window to avoid wasting time?
Can I rather answer the first part of the question? Actually, it's not that time-consuming because there are factorization. Like for the exponential weighted average methods, you only need to remember the cumulative losses of each expert. So you need to maintain capital N weights. So that's okay. I mean, you don't need to remember the whole data. You can summarize them. And same for Ridge, actually, there are recursive formulas. So we never encountered these computational issues.
Okay. Thank you. Other remarks? Yeah.
Yep.
Using the for the question of exchange rates, did you try to compare the performance of the methods with the performance, for example, of the exchange rate of the forward contract for 1 month from now?
No, because we really want to do something economic and not financial. It's because I'm working with a macroeconomist for that, and the point was to take a look at the Mies and Rogoff 83 paper, the first econ paper on that, macroecon paper on that, and show that the result can be saved, actually. So we actually weren't interested in really improving, in really making good forecast, but we were interested in making good forecast under the constraints of only resorting to some economic fundamentals with the aim to show that these economic fundamentals convey some information which was deemed a lost cause in macroeconomics.
Other questions? Okay, so let's thank Gilles again.